Cathode ray oscilloscope. By the end of this lesson, you should be able to explain thermionic emission, describe the properties of cathode rays, describe the working principle of the cathode ray oscilloscope. How are pictures formed on the screen? What enables us to see the pictures on the screen? What kind of information can we get from the graph on the cardiograph screen? Of a metal contains a large number of free electrons. What are free electrons? In metals, each atom has a few loosely attached outer electrons which are free to move near the surface but remains inside the metal. If one of the free electrons near the surface of the metal tries to escape, it will experience an attractive force from the atomic nuclei near the surface. Thus, the electron cannot escape. When metals are heated, the kinetic energy of the electrons increases. Some electrons gain sufficient kinetic energy to escape from the metal. What is the name of this process of electron emission? The process of emission of electrons from a heated surface of a metal is known as thermionic emission. This is a vacuum tube. The vacuum tube consists of a tungsten filament, a cathode, and an anode. The filament is connected to a 6-volt power supply. The cathode is connected to the negative terminal, while the anode is connected to the positive terminal of a high-voltage DC power supply of 4 kilovolts. A milliammeter is also connected in the circuit. Click on switch S1. What happens to the milliammeter pointer? The milliammeter pointer does not show any deflection. What does this indicate? The non-deflection of the milliammeter pointer indicates that the circuit is not complete. Thus, there is no current flow. Click on switch S2. What happens to the milliammeter pointer now? The milliammeter pointer shows a deflection. Why? The deflection of the milliammeter pointer indicates that there is a current flow in the circuit. Thus, the circuit is complete. When S1 is switched on, current from the 6-volt power supply flows and heats up the filament. The filament then heats up the cathode. Free electrons from the surface of the cathode gain kinetic energy. Electrons that gain sufficient kinetic energy are able to escape from the surface of the cathode. The high potential difference between the cathode and the anode causes the electrons to accelerate towards the anode. As electrons from the cathode reach the anode, the circuit is completed. Hence, there is a current flow. What happens to the milliammeter pointer when the polarity of the terminals of the power supply connected to the cathode and anode is reversed? Click on switch S1. Click on switch S2. The milliammeter pointer does not show any deflection. Why? When the filament is heated, electrons on the surface of the anode gain kinetic energy. However, since the cathode is also negatively charged, free electrons on the surface of the anode are not attracted by the cathode. Hence, there is no flow of electrons from the anode to the cathode, resulting in no flow of current. Thus, there is no deflection of the milliammeter pointer. What can you say about the fermionic emission? Fermionic emission occurs when electrons have enough energy to escape from the surface of a heated cathode. The stream of electrons emitted from the cathode is also known as cathode ray. Circuit consisting of a Maltese cross tube and an extra high tension EHT DC supply has been set up. The Maltese cross tube consists of a filament cathode, an anode, a Maltese cross, and a fluorescent screen. The 6-volt power supply is connected to the filament. The positive terminal of the EHT is connected to the anode and the Maltese cross, while the negative terminal of the EHT is connected to the filament, which is also the cathode. Click on switch S1. What do you see on the screen? A dark shadow of the Maltese cross surrounded by yellow light is seen on the screen. Why? The shadow is formed because the light ray from the glowing filament is blocked by the Maltese cross. How does light ray travel? Light ray travels in straight lines. Switch on the 3 kilovolt EHT DC supply. What do you see on the screen? A darker shadow of the Maltese cross surrounded by green light is seen on the screen. Why? The shadow is formed because the streams of electrons emitted by the hot cathode are blocked by the Maltese cross. The shadow formed is of the same size and at the same position as that formed earlier when only the filament glows. Electrons which are not blocked by the Maltese cross strike the fluorescent on the screen and green light is emitted. The streams of electrons are also called cathode ray. How does cathode ray travel? Cathode ray travels in straight lines. What happens to the shadow of the Maltese cross when a magnet is brought near to the tube? The darker shadow of the Maltese cross is deflected downwards. What does this indicate? This indicates that the cathode ray can be deflected by a magnetic field. The direction of deflection can be determined by using Fleming's left-hand rule. The forefinger should point in the direction of the magnetic field. The second finger points in the direction of current flow, that is, in the opposite direction of electron flow. The thumb will point in the direction of the force on the cathode ray, which is indicated by the deflection of the shadow of the Maltese cross. Determine the direction of deflection of the cathode ray when the polarity of the magnet is reversed. When the south end of a magnet is brought near, the shadow of the Maltese cross is shifted upwards, indicating that the cathode ray is deflected upwards. The cathode ray can be deflected by a magnetic field. The direction of deflection of the cathode ray can be determined by using Fleming's left-hand rule. A circuit consisting of a deflection tube connected to two extra high-tension EHT supplies has been set up. The deflection tube consists of a filament cathode, an anode, a fluorescent screen, and a pair of horizontal metal plates. Click on S1 and S2 to switch on the 6-volt and the 3 kV power supplies connected to the tube. What do you see on the screen? A horizontal line trace is displayed on the screen. What does this trace indicate? The horizontal line trace indicates that the cathode ray travels in a straight line. Click on S3 to switch on the EHT power supply to the horizontal metal plates. What can you say about the path of the cathode ray? The path traced is a parabola. This indicates that the cathode ray can be deflected by an electric field. Deflection of the cathode ray towards the positively charged plate shows that the cathode ray is negatively charged. These charged particles are called electrons. What will happen to the cathode ray if the EHT supply connected to the metal plates is reversed? The path traced is still a parabola, but now the cathode ray is deflected downwards towards the positively charged plate. The cathode ray can be deflected by an electric field. The cathode ray is deflected towards the positively charged plate, thus the cathode ray is negatively charged. State the properties of the cathode ray. The properties of the cathode ray are summarized as follows. 1. Cathode ray travels from the cathode to the anode in a straight line. 2. Cathode ray has high kinetic energy. 3. Cathode ray can cause certain substances to fluoresce. 4. Cathode ray is made up of negatively charged particles called electrons. 5. Cathode ray can be deflected by an electric field. 6. Cathode ray can be deflected by a magnetic field. This is the structure of a cathode ray oscilloscope, CRO. There are three main components of the CRO, namely 1. Electron gun, 2. Deflection system, and 3. Fluorescent screen. Electron gun. The electron gun is used to produce streams of electrons. The electron gun comprises 1. Filament, 2. Cathode, 3. Control grid, 4. Focusing anode, and 5. Accelerating anode. Click on switch S1. What happens to the filament? When current flows, the filament becomes hot and heats up the cathode. When the cathode is heated, free electrons at the surface of the cathode gain kinetic energy. Click on S2 to switch on the EHT supply. What do you see on the screen? A bright green spot is seen on the screen. How is the brightness of the spot controlled? Click on the Control Grid Voltage button and vary the voltage to see what happens. The control grid controls the number of electrons emitted, thus affecting the brightness of the spot on the screen. When the grid is more negatively charged, the number of electrons allowed to be emitted from the electron gun is decreased, and thus reducing the brightness of the spot on the screen. There is another way of controlling the brightness of the spot. Click on the Accelerating Anode Voltage button and vary the voltage to see what happens. The accelerating anode is used to accelerate the electron beam towards the screen. By increasing the voltage of the accelerating anode, the electrons hit the screen with an increased kinetic energy. Thus, the amount of kinetic energy that is converted to light is also increased. Hence, the brightness of the spot increases. How do we control the sharpness of the bright spot? Click on the Focusing Anode Voltage button and vary the voltage to see what happens. The focusing anode focuses the electrons leaving the cathode to a narrow beam, so that they arrive at the smaller spot on the screen. Click on the Focusing Anode Voltage button and vary the voltage to see what happens. Deflection system. How does the deflection system function? The deflection system consists of two sets of parallel plates. The Y plates are used to shift or deflect the electron beam vertically, and the X plates are used to shift or deflect the electron beam horizontally. How do we control the position of the bright spot? Click on the Voltage of the Y plates button and vary the voltage to see what happens. Then click on the Reverse Polarity button to reverse the polarities of the Y plates. Click on the voltage of the X plates button and vary the voltage to see what happens. Then click on the reverse polarity button to reverse the polarities of the X plates. Fluorescent screen. The screen is coated with zinc sulfide. Zinc sulfide fluoresces and emits green light when the electrons strike it. The kinetic energy of the electrons is converted into light. What is the speed of an electron when it hits the screen? The kinetic energy of the electrons is equal to the electrical energy supplied by the power supply across the cathode and anode. Thus, the kinetic energy of the electron, half mv squared, is equal to the electrical energy eV. Then, the speed of the electron is the square root of 2eV divided by m. What happens to the kinetic energy of the electron when it hits the screen? When an electron hits the screen, its kinetic energy would be converted into light and heat. Why must the space inside the CRO be a vacuum? The space inside the CRO must be a vacuum to prevent the electrons from colliding with other particles. Hence, the electrons will be able to strike the screen without any energy loss due to collisions. Switch off the CRO. Mouse over each knob of the CRO to know the function of each knob. Time base, time per division, controls the magnitude of the horizontal deflection of the bright spot by adjusting the frequency. X input, a terminal to connect the potential difference across the X plates. Earth, to earth the input terminal. AC-DC switch, selects the type of input received. DC displays waveform of DC and AC potential differences. AC displays waveform of AC potential difference only. Y input, a terminal to connect the potential difference across the Y plates. Y gain, volt per division, controls the magnitude of the vertical deflection of the bright spot by adjusting the amplitude. Y-shift adjusts the vertical position of the bright spot. X-shift adjusts the horizontal position of the bright spot. Focus focuses the bright spot on the screen so that it is sharper. Brightness controls the brightness of the spot on the screen. This is the whole structure of the CRO. The main components of the CRO are 1. Electron gun, 2. Deflection system, and 3. The fluorescent screen. The filament is used to heat the cathode. Free electrons that gained enough energy are able to escape from the surface of the heated cathode. Emission of electrons through this process is called fermionic emission. The control grid controls the number of electrons reaching the fluorescent screen, hence controlling the brightness of the spot on the screen. The focusing anode focuses the electrons or the cathode ray onto the screen. The accelerating anode accelerates the electrons to high speed. Thus, the electron gun produces a narrow electron beam that has high kinetic energy. The electron beam produced by the electron gun then passes through the deflection system. This system consists of the Y plates and the X plates, which can deflect the electron beam either in the vertical or horizontal direction, respectively. When electrons with high kinetic energy strike the fluorescent screen, the material on the screen fluoresces, and the kinetic energy of the electrons is converted to heat and light. Click on the correct answer. What is thermionic emission? Click on the correct answer. Which of the following figures shows the correct path of the cathode ray or electron beam in an electric field? Click on the correct answer. The diagram shows the fluorescent screen of a Maltese cross tube. In which direction will the shadow of the Maltese cross move when the magnet is brought close to it? Click on the correct answer. Which of the following controls the brightness of the spot on the screen of a cathode ray oscilloscope? Click on the correct answer. The potential difference between the filament and anode is 4 kilovolts. What is the maximum speed of an electron when it hits the screen? Mass of electron, m equals 9 times 10 to the power of minus 31 kilograms. Charge of electron, E equals 1.6 times 10 to the power of minus 19 coulombs. Cathode ray tube, CRT, is an important component in conventional television sets and computer monitors. The CRT was invented by a German physicist, Carl Ferdinand Braun, in 1897. Three main components of the CRT are the electron gun, a deflection system, and a fluorescent screen. The electron gun, placed in the rear of the vacuum tube, is used to generate electrons. A positively charged grid mounted in front of the electron gun focuses and accelerates the electron beam towards the screen. The inside face of the screen is lined with a layer of material called phosphor, which has the ability to fluoresce. Phosphor absorbs energy from the electron beam and converts this energy into light. The spot where the electron beam hits the screen will glow. Varying the intensity of the electron beam will vary the intensity or brightness of the spot. An electrical potential applied across the vertical deflection plates, or the Y plates, will cause the electron beam to be deflected vertically. If the upper plate is positively charged, it will cause the beam to be deflected upwards. Hence, the bright spot on the screen will move upwards. Conversely, if the lower plate is positively charged, the bright spot on the screen will move downwards. Similarly, two horizontal deflection plates, or the X plates, are used to move the spot either to the left or to the right of the screen. By combining the effects of the vertical and horizontal deflection plates, we're able to guide the spot to any point on the screen. There are several ways in which we can manipulate the bright spot to create pictures on the screen, but by far the most common is the raster scan technique. Using this technique, the electron beam begins in the upper left corner of the screen and is brought across the screen to the right. The path of the beam as it crosses the screen is called a line. When the beam reaches the right-hand side of the screen, it undergoes a process known as horizontal flyback, in which its intensity is reduced, the topmost pink line. While the beam is flying back, it is also shifted slightly down the screen. The beam is now used to form a second line, then a third, and so on until it reaches the bottom of the screen. The number of lines affects the resolution of the resulting picture. British television is based on 625 lines, while the American television system uses only 405. When the beam reaches the bottom right-hand corner of the screen, it undergoes vertical flyback, in which its intensity is reduced. It flies back up the screen to return to its original position in the upper left-hand corner, diagonal black line, and the whole process starts again. Thus, we can create pictures by varying the intensity of the beam as it scans across the screen. For example, consider how we can construct the image of a simple triangle. Note that this small group of lines represents a tiny area located somewhere in the middle of a much larger screen. In the real world, the lines forming the picture would be very close together, so this would actually be a very small triangle, but it serves to illustrate the concept. When they are first introduced to this technique for creating pictures, many people wonder why they can't see the lines being drawn and why the image doesn't appear to flicker. The answer has three parts. 1. The electrons forming the electron beam travel at a tremendous speed, and the beam itself can be manipulated very quickly. The beam used in a television set can scan the entire picture in a fraction of a second, and the entire picture is actually redrawn approximately 30 times a second for American NTSC format televisions, or 25 times a second for European PAL systems. 2. The phosphor lining the inside of the screen is carefully chosen to fluoresce for exactly the correct amount of time, such that any particular point has only just stopped fluorescing by the time the electron beam returns to that point on its next scan. 3. The combination of our eyes and nervous system exhibit persistence of vision, which means we continue to see an image for a fraction of a second. All of these effects combine to form a seemingly substantial picture on the TV screen or computer monitor screen. Mouse over the labels on the graphics to know more about the CRT. lesson, we learn that 1. Fermionic emission is the process of electron emission from a heated metal surface. 2. Cathode ray oscilloscope has three main components: A. The electron gun, B. The deflection system, and C. The fluorescence screen. 3. The properties of the cathode ray are summarized as follows. 1. Cathode ray travels from the cathode to the anode in a straight line. 2. Cathode ray has high kinetic energy. 3. Cathode ray can cause certain substances to fluoresce. 4. Cathode ray is made up of negatively charged particles called electrons. 5. Cathode ray can be deflected by an electric field. 6. Cathode ray can be deflected by a magnetic field.